This video is about understanding the mass spectrum data that we collected for Lab 1. And in particular, what I want to point out is in all mass spectra, what you see usually is something like this, where there's a peak on the far right that is actually the most interesting peak in many ways. It is the molecular ion peak, or alternatively, the peak that corresponds to the mass of the compound, either plus sodium or plus hydrogen in the case of ESI. If we're dealing instead with GCMS, then it will be the mass of the compound itself, where you have simply knocked an electron out of the system and left it charged. In any event, the peaks on the far right are the ones that correspond to the greatest mass of the compound, which is to say the molecular structure itself. Then, because the molecule is at relatively high energy and unstable, it will have a tendency to want to fall apart into various smaller fragments. And with ESI, this is a relatively minor component of the information. You care mostly about these two peaks over here on the right. But with gas chromatography mass spectrometry, GCMS, then we're using a different ionization method, and the compound will tend to fall apart. And so there's information contained within this peak on the right, and then this fragmentation pattern that you see all throughout also contains some information. To a first approximation, though, the information I really want you to take away from a GCMS or an ESI mass spec is what is the peak that's the furthest right, and does that make sense? So in this particular molecule, once you add up what it all should add up to, you get two different numbers, 232.0 for the chlorine 35 isotope and 234.0 for the chlorine 37 isotope. This information that I'm talking about with the isotopes of chlorine shows up in the background information that I gave you in the lab packet. So if you're not making sense of this, try reading the background information in the lab packet. You will note that what I have here is a 232 line and another line which is not labeled by the instrument but which comes at 234, and roughly what I have is a 3-to-1 height difference between the 232 and the 234 lines, which makes sense because we have chlorine with both the 35 and 37 isotopes. The natural 35 isotope is present with 3 times higher intensity than the 37 isotope, and that's why you get this pattern 3-to-1. As this molecule starts to fragment, one thing you'll notice is that this isotope pattern is retained in a couple of the other fragments. So you'll notice that this 188 line also has a corresponding 190 line. This 160 line has a corresponding 162 line. By the time you get to the 125 fragment, whatever has fallen off this molecule includes the chlorine. The chlorine is gone in here, whereas the chlorine is present in the molecular ion fragments and these fragments as well. The message for starting material 1 really is that there are two main fragments corresponding to the molecular ion itself. 232 is the 35 chlorine, 234 is the 37 chlorine. And the presence of both of those says that you have the right molecular ion, the right mass of starting material 1 present. Intermediate C likewise contains the same sort of chlorine isotope effect. There's a 315.1 chlorine isotope that corresponds to 35 Cl. There's also a 317.1, not labeled by the instrument, but it's there, corresponding to 37 Cl. You will notice that this pattern shows up again, particularly in the 231-233 pair, and also in some of these other ones. But you'll notice that some of these fragments that are down here contain different isotope patterns, don't appear to have the chlorine present anymore. Again, the main lesson is that intermediate C contains the expected isotope pattern for chlorine, as it should, because the molecule itself contains a chlorine. In addition, the mass of intermediate C is precisely what you'd expect for the molecular ion, 315.1 and 317.1. With the desired product, what we see now is that there is no corresponding isotope effect happening here. This is a 380.3 line, and this is a 381.3 line. So there's no chlorines present for the product, and that makes sense because the chlorine has now been replaced by this hexylamine side chain. So the molecular ion is now quite a bit heavier, 380.3, because we've added this chunk, and in addition, it no longer contains the chlorine isotope effects. And you don't actually see the chlorine isotope effects showing up anywhere else. Again, the mass spec lesson for product itself is the molecular ion corresponds to the mass that we would expect, and there is no chlorine isotope effect present with the product. Intermediate A and B spectrum is a bit different because the instrument is a bit different, but the idea remains the same. 356 and 358 are present for the mass plus sodium peak corresponding to 35 Cl, and the mass plus sodium peak corresponding to the 37 Cl is the 358.2. Similarly, the mass of the M plus plus peak would be 334 with 35 Cl, and then there's an additional peak in there at 336, which corresponds to 37 Cl with a proton bound. When you do ESI mass spec, you don't actually see the molecular ions themselves. You see an M plus H, which is to say a proton is bound somewhere, or an M plus sodium peak, which means that a sodium is bound somewhere. That's what you tend to see with the ESI type mass spec. But I'd like you to focus your attention much more on the mass spec for the product and for intermediate C. And in particular, what you're looking for is the absence of isotope effects and the presence of the correct molecular mass for the product. In addition, you should notice that intermediate C has a mass that's quite a bit smaller than that of the product, but does seem to contain this 3-to-1 ratio of 315.1 to 317.1. Therefore, it contains a chlorine. And that makes sense because intermediate C should be smaller and contain a chlorine, where product should be bigger and should not have a chlorine.